All right, so let's get started. So it's, okay, quiet down, please. So it's Friday before a nice weekend, so I think today we're going to do something not too complicated. And then when we get back from our all rested from our weekend, we'll pick up Monday on something a little more complicated. So just quickly in the news, you know, one of the things that we've been telling you in this class is that PCs are going away, right? That computing's moving, you know, to the edges, you know, to the extremes, either you know, something in a data center or something you can carry. And a lot of the evidence that you're seeing were things like, you know, big companies like IBM getting out of the PC business. HP made a big announcement that they were getting out of the PC business. But they just recently announced that they were just kidding, and they're actually not going to get out of the PC business. And, you know, it's a good reminder that when we talk about trends, especially at the university, you know, when we're kind of one or more steps removed from what's really going on, it's easy to sort of say these big statements like that PCs are going away. But, you know, if you look at what's going on here, these, you know, HP was, this is their quarterly revenue from their PC business. It was about $10 billion, right? So that's just one company. So it's a pretty big business, and it wasn't something that they wanted to get rid of lightly, at least after when they fired the old CEO and hired the new CEO. The new CEO came in and said, "What are you doing?" Anyway, so just kind of a reality check that you know, PCs aren't going away right away. Can you guys just keep it down a little bit? And on the other hand, you know, this is kind of from a business point of view. You know, PCs, the profits on PCs are shrinking, and you know, it's going to be hard for companies to compete. So anyway, just a reality check. Okay, so what we're going to do today is we're going to continue on that path that we've been going. Right, we went all the way down to the bottom of the stack. We started talking about transistors, built up to gates, built up to bigger circuits than that. And so now what we're going to start doing is putting together the actual CPU. And that's what we're going to do. So, all right, so here's what we talked about last time. We looked at, you know, this one type of circuit called a MUX, or a multiplexer. It's really kind of a data selector, that you have a bunch of data lines coming in, you have a bunch of control lines coming in, and then based on the way those control lines are set, one of the data inputs gets to pass through, okay? And basically, each input can be, you know, n bits wide. So, you know, there's one question of how many inputs are you multiplexing across, and the other is how wide those are. So you can have multiplexes that are taking 32-bit quantities and multiplexing many of those, okay? And again, this multiplexer word is a little weird. Think of it as a selector. Right, one of those gets to pass through. We talked about how those things can be built and how you get to put them together. And then we said we moved up a level in complexity, and we said, okay, now let's talk about how to build the real circuits that do real work. And we talked about the ALU, the arithmetic and logic unit. And we looked at how you build that, again, with this kind of selector idea where based on the input, it's either an adder or a subtractor or a shifter or, you know, or whatever. And so we talked about how that got put together, and then we looked at this one particularly cool case of how you can build an adder and a subtractor out of the same circuits, right? And we had this whole idea with the carry in and the carry out, and then looked at, you know, a convenient way of implementing a subtractor just by having the ability to sort of conditionally invert one of the inputs, right? Turn it negative, okay? So that's where we were. And what we're going to do today then is we'll say, okay, great. So now we know how to build the circuits. Let's talk about how those circuits get put together so that you can actually execute all these instructions that we've been learning about. So we're actually going to build a MIPS processor, all right? And so today we're going to just, at sort of a very high level, talk about how that thing's going to be put together. And then we're going to look at how certain instructions are going to use the stuff that we put together. So, and this is at a real high level. You know, these are the main components of the computer. And basically, we're going to be looking at this stuff today. So this is the processor, and we're going to look at two parts of it, sort of the data path, which is how the voltages flow through the different circuits, and the control, which is what makes those voltages go in the directions they go in, and why that ends up doing the calculation you want it to do, okay, or executing the instruction you want. Don't forget that's just part of the system. So out here you have disks and things like that. You have input-output. You have programs live here when they're not being run. When you want to run them, you load them. They get loaded into memory, and then the processor is going to be pulling things out of memory. At least it's going to be pulling instructions out of memory to execute them, bringing them up through the cache hierarchy, and then it's going to be writing data out there as well. But what we're not going to be doing, by the way, is we're not going to be writing instructions. So the only time that instructions get written into memory in our model is when you first load the program. That brings the instructions to memory. At that point, our instruction memory is read-only, okay, and that's key. That's key to something to keep in mind. All right, so what are the pieces? So the CPU is the processor, right? Central processing unit. That's the thing that actually does all the work. The data path is sort of the muscle, right? It's sort of the kind of the lowest level plumbing of what's going on. And then the control is the brain. That's what's determining how things actually flow through all that elaborate plumbing that you've constructed. Okay? Okay, so here's kind of the key idea that we want to get through today, is that what you want to do, we're going to look at a single, today we're going to look at a single instruction execution, okay? So we have, and we're going to be thinking at kind of the MIPS instruction level. So, you could conceive of building a bunch of circuits that could, each individually execute a given MIPS instruction, or maybe if you were clever, you could put a couple of them together. Okay, but you could think about building sort of a box that just implements an instruction. All right, but what we're going to do instead, to do that, you'd be replicating a lot of logic. It would be inefficient. It would be big, and it would be really kind of hard to do. And so what we're going to do is we're going to break instruction execution into a sequence of steps or stages, and then we're going to put those stages together in various ways to execute the instructions that we want to execute. Okay, and this, kind of going along with our philosophy of simpler is better. These stages, because they're smaller, are going to be easier to design, and because we have this ability to kind of take these stages and put them together, that gives us some optimization opportunities as well. So it's really kind of an engineering decision that we're going to build this multi-stage data path. Okay, and then in a couple lectures, we'll talk about how we take advantage of that to get even more parallelism out of the system. But we're not going to talk too much about that today. Okay, so this is it. So this is really the key idea, which is we've decided to break, at least in the MIPS processor, we've decided to break the processor or the data path into 5 stages. And these are the 5 stages. First, you get the instruction. That's stage 1. Then you decode it. You figure out what that instruction is telling you to do. That's stage 2. Stage 3 is you run it through the ALU, which we designed last class. So that actually does the work. Sometimes you need to access memory. Okay, so that happens in the 4th stage of our pipeline. And then every once in a while, you have to write things to memory. And that happens in the 5th stage. Okay? So what I want to do is go over each of these stages in a little more detail. And then I want to say, okay, let's look at a few different instructions and how they live in these stages. Okay, so so the first stage is you got to get the instruction. Okay, so remember in MIPS, instructions are going to be 32 bits. So what we're going to do is we're going to have to fetch the 32 bits that represent our instruction from memory. Now, how do we know the address of the instruction that we want to run? How do we know that? Yeah, it's a PC, right? It's in the program counter. That's the address of the next instruction that we're going to run. Okay, so we have to be able to pull that instruction in from memory. Okay, do we really want to have to pull it in from memory? No. Why? Because that takes us 100 clock cycles minimum, and we don't want to wait for 100 clock cycles, right? We're just starting to run an instruction. The last thing we want to do is wait for 100 clock cycles. So what we're going to do is we're going to look in our cache, and if we did a good job of building our cache, the instruction is going to be right there. And remember, in level 1 cache, we can return that within the time we need to be able to get through this whole pipeline, this whole set of stages in a single clock cycle. Okay, so that's why level 1 has to be fast. So we're going to get the instruction out of memory, hopefully out of level 1 cache. And we're also, by the way, going to get ready to run the next instruction. How do we do that? Well, we increment the program counter. How do we increment the program counter? Well, it's easy because all of our instructions are 32 bits. And so we just add 4 to it, right? 4 bytes. Okay, and that tells us that gets the PC ready to get the next instruction. Now, can anyone think of a reason why that might actually not be a useful thing to do? Yeah, in the back? Yeah, jumps, branches, any sort of conditional. You don't actually know that the next thing you're going to do is that next instruction. Okay, but that's your best guess. So you get that set up. Okay, but remember, as we're building this pipeline, we've got to think about how to build it in a way that we can handle these conditional operators that might take us to a different part in the instruction flow. Okay, and remember, again, if we take a big jump somewhere, it might not be in our level 1 cache. That's going to slow us down. There's some issues there, too. Okay, so that's where some of the fun is going to come in designing this thing. Okay, so that's step 1. Bring the instruction in, increment the PC counter. Stage 2 is we say, okay, I just read this 32-bit quantity. What is that? What's that telling me? So we're going to decode that instruction. Okay, and you guys have already done a fair amount of this in your labs and projects. And, if you look at the green sheet, that tells you, the first, these many bits or the high order this many bits are the opcode. The opcode, is going to tell us which operation it is. And then based on that opcode, I know that my instruction is one of 3 or however many formats the MIPS instructions have, hopefully not too many. And then based on that, I'll pull out the rest of the bits from that instruction and figure out what they are. Are they registers? Are they immediate values? What else are they? So we're going to fetch the instruction, and we're going to gather the data that we need for that instruction. So we're going to read the opcode, going to figure out what the rest of the instruction looks like in terms of each portion of the rest of the 32 bits. And then we're going to read the data that we need. So if it's something like an add instruction, that means that there's going to be 2 registers there, right? The names of 2 registers. If it's an add immediate, then we know there's going to be 1 register that we have to read. Okay, and then there's an immediate value. And if it's something like a jump, then there's, we don't have to read anything, right? We're not looking at any registers. Okay, so after stage 2, we know what instruction we're running, and we've pulled out, the registers and the immediate values that we need, that were encoded into that instruction. And I'm going to show examples of all this in a second. Stage 3, that's when we actually do the work. So we go to the ALU, and again, that's where we're doing our arithmetic, we're doing shifting, we're doing bitwise, logical operators, we're doing comparisons. All that happens in this stage, in the ALU. But there's also some other stuff that can happen in this stage, too. So for example, what about an instruction like a load? Okay, so here, what do we have here? Well, we've got, we're going to load into this register, and the address that we're going to load is what? It's the address that's in T1 plus 40, right? This is this offset-based addressing. Okay, so in order to calculate that address, what are we going to have to do? We're going to have to do an addition, right? Because the address we want to load from is what's in that register plus 40. Okay, how do we do additions? We use the ALU. So guess what? We're going to use the ALU to help calculate the address that in this case we need to load from. So the ALU is doing things like manipulating quantities that are in registers, as you'd expect, but it's also doing a lot of the work for the addressing modes that we have, too. Okay? So that's kind of an interesting thing. So, so if there's addition that needs to be done to figure out the address, we're going to do that in this stage of the pipeline as well. Okay? All right. More than halfway done. So stage 4. Stage 4 is memory access. Which operations have to access memory? Yeah, loads. For sure. Stores do, but I think we do that in the next step, the next stage. That might be it, actually. Okay, well, it says store does too. All right, so we'll see. So load and store have to do stuff with memory. If you're an instruction other than load or store, you're going to actually just not do anything during this part. You're going to skip this stage or just stay idle. Okay? So it depends on how you've implemented your processor. Okay? So, okay, now how long is this access stage going to take? So remember, we're building what we're calling today, we're building what's called a single cycle CPU, which means instructions should be able to run in this whole 5-stage process should be able to run in the length of a single clock tick, right, in a clock cycle. Okay? So, how long does this memory access take? And as you guys already said, the answer is, well, it depends, right? If things are in the cache, it happens right away, and if things aren't in the cache, it could take 100 clock cycles if you have to get it from memory, and if it's out on disk, even worse. If you go to memory and it's not there for some reason, which we'll talk about when we talk about other types of memory systems, you might have to wait for it to come in from disk. So this one can take a long time, okay? But if you're an operation that's not a load or a store, you'll just blast through this one, okay? And so, the only way we're going to get good performance out of our processor is if the cache system is doing what it's supposed to do, right? Which is returning us the answers we need quickly. All right, great. Then we're done to the last stage of the data path, which is you got to write the registers. And, okay, I'm sorry. So let me just make sure I didn't mess you guys up with my own confusion. So the reason store is in stage 4 is because if you have to write something to memory, we're going to do it in stage 4. Okay? So stage 4, if you're a load, we're going to bring it in from memory. If you're store, we're going to write it out to memory. And if you're anything else, we're just not going to do anything during this stage. Okay? Stage 5 is a write, but it's not to memory, it's to registers. So, a lot of times when we're doing a calculation, what do? We do the calculation and we write the result into a register. And so, anything with arithmetic or most of the operations we're doing in the ALU, those things, the result of that's getting stored into a register. And so for those guys in stage 5, we take the result, we put it in a register. And for anything else, we either remain idle or we skip it. Okay? All right, so 5 stages. Everybody does the first 3. Some do the 4th, some do the 5th. Okay, so that's what it looks like when you put it all together. Okay, so this is our generic data path, and it's best if you read it from your left to your right. And so basically, in the first stage, we're gonna get the instruction from the memory. Second stage, we're going to decode that instruction, figure out what it means, and we're going to get the register values that we need. Because remember, registers are stored in this thing called the register file, okay? And you index into the register file based on, in the MIPS architecture, there's 32 registers. Based on the number of that register, you go to that entry in the register file and you pull out the value. Okay, that's how we get the register values. Then we're going to execute using the ALU. If we have to write to memory or read from memory, that happens in stage 4. And then finally, we go back and we write the registers that we have to. Okay? And this picture is missing some arrows. Yeah, question?
So stage 2, when you read the data from the register,
Uh-huh.
where does the data from the register?
So good question. So the question is, when I'm reading data from the registers, where does it get stored? And it gets stored in stateful circuits that are going to be used by the ALU. So you can actually pull them into a part of the ALU if you need to. All right. So good. So let's look at a few different instructions and how they work their way through this 5-stage pipeline. So let's start off with an add. So an add is basically going to say, stage 1, we got to get the instruction. We always do that. We increment the PC. We add 4 to it. Stage 2, we look at it and we say, hey, I know what that opcode is. That opcode is an AND. Okay, and since it's an AND, I know what follows is going to be the register that I'm going to put the answer in, and then the 2 registers that I'm going to add together. Okay, so there's going to be 3 register numbers in there. Okay, so what I'm going to do is I'm going to read in stage 2 the value for register 1 and the value for register 2. Those are the things I'm going to add together. Stage 3, right, I hand those over to the ALU. In stage 3, they get added. Okay, stage 4, which is where you go to memory, we just do nothing because there's no memory access here. And then stage 5, we write the result into the register, okay, into register 3. Okay, so an add or an arithmetic operation like that is going to use stages 1, 2, 3. It's going to skip stage 4 or stay idle, and then it's going to do stage 5. Okay, and what that looks like more or less, and this is kind of a weird animation, but basically, we're going to use the PC to tell us what instruction to fetch from memory. We're going to hope that it's in the level 1 cache, so it happens quickly. Okay, we're going to, while we're there, we're going to add 4 to the PC. Okay. Then, in this case, we know that we need, we're interested in 3 registers. Okay, so we figured that out because we've decoded the instruction. Okay, we're going to take the values that are in the register file for register 1 and register 2, and we're going to send those over to the ALU. Okay, so in this case, I don't think they're going to get stored. I think they're just going to get sent to the ALU. And then in stage 3, we're going to do the addition. Okay, that's going to give us our answer. Here's where the animation gets a little weird, so just keep an eye on this. Stage 4, we're doing nothing, and nothing got represented this way. And then in stage 5, we write to register 3. Okay, so the thing I want you to just keep an eye on here, and I couldn't figure out a better way to do this animation, it's kind of looking like this write is happening through the memory, but it's not. The write goes from the ALU into the register. Okay, and stage 4 is just, it's blank. Okay, so that's supposed to be saying that it just passes through. Okay, so just keep an eye on that. Make a note on your notes if you have to. Yeah. I'm sorry? The third line, this one here? Yeah. Okay, this line here is the immediate line. And so remember, we have certain instructions that have a value in the instruction. We're going to use it for that. Okay? And the last thing we do, last thing we do is we're going to be able to add 4 to the PC. So you got to, we already incremented the PC. That again should also happen at that first. That happens in the first step. Okay? But that's the basic flow, right? At this point, after we've written the register, the next thing we do is the PC has already been incremented. We go look in memory, get that next instruction, and start again. So yeah, please. Yep. Oh, okay. So how does it know which register it's writing to? That's okay. So we're going to do this in 2 steps. In the first step, we're sort of showing the basic flow, right? Kind of the plumbing. What we're going to talk about in class on Monday, which is going to be more complicated than this, is what's called control. And the control is going to show you the signals that get set, that get turned on and off, so that the data actually comes from the right place and goes to the right place. So, basically, when at the end of during the 5th stage, when you're writing back to that register, there's actually going to be a signal that gets set that makes sure that the write, when it happens to the register, when you write into the register file, the one register that gets updated is this one right here. So, but that's part of control, not really part of this. Yeah, you had a question. Yep. Okay, so good. So the question was, if we're sitting idle, okay. So if in something like an add where we're skipping the 4th stage, if we're not skipping it but we're just remaining idle, do we stay idle for a clock tick? And the answer right now is no, because what we're building here is what I said earlier is a single cycle CPU. So the length of a clock tick is big enough to include all 5 stages. So there will be a delay, but it will be within the context of a clock tick. So it doesn't cost you any extra clocks. We'll look at a different version of this where that could happen. Okay, but for single cycle CPU, this whole thing is going to finish within a clock cycle unless there's a memory stall. Yeah. Yep. Yep. Okay, so the question is, when I write to the register in stage 5, is it possible that I could have clobbered something that's in memory? Yeah. Yeah, okay, so so this is a good question. If you've got an instruction to load a register, say R3, and then you're running this instruction where we're adding, and the result of that add should end up in R3, can we get into trouble? And in this CPU, no, because we're doing each instruction completely until we do the next one. Okay? So right now, we don't have any parallelism of instructions. So if you're going to do a load into R3, and then you do an add, where the result goes into R3, yes, that's going to overwrite the load, but that's what your program wants to do, right? Because you put the load and then you put the, if that's not what you wanted, then that's a bug in your compiler or in your program. Okay, but there's no sort of timing problem here because it all happens within a clock tick. First instruction completely finishes, then you start again. Then you go on the next instruction. All right? Any other questions about this? It's kind of a funny way we're teaching it here because, there's a bunch of the story that we're not telling you yet. So there's a few things you're probably wondering, how's that really work? And, and the answer is, we're going to have to wait a lecture or two till you really get to it. And that's what Dan was talking about with his, to me, kind of unsettling story of the sandwich that you're eating with only half a jaw. But that's what he meant, is we're sort of putting it together, and at some point, boom, you get it. It all comes together. And we're getting close. It's going to be, next lecture or the lecture after. All right. So SLTI, does anyone remember what that instruction does? It's set if less than immediate. And I had to look it up. But basically what that's going to do is it says if R1 is less than 7, then set R3 to 1. Right? Otherwise, leave it alone. Okay? So if you think about this, what's it doing? It's not doing any memory access. Okay? So we're not going to have stage 4. Is it writing any registers? Well, it could. Right? Depends on how the test comes out. So, stage 5 can happen here. Okay? And so this is really what's going to happen. You get the instruction from memory. You look up the opcode in your little green, the computer has its own little version of the green sheet. It says, hey, this is an SLTI. I used to remember what that was. Oh, yeah, that's set less than immediate. Now I know that what I'm going to have after that is a register that's going to be my result, a register that I'm going to compare, and an immediate value that I'm going to compare it to. Is there a question in front? Okay. So, so then in stage 3, I'm going to do that comparison. Okay, the ALU is going to do the comparison, right? And stage 4, we're not touching memory, so that nothing happens. And stage 5, if the test evaluates to true, we're going to write register 3. Otherwise, we're not going to do anything. Oh, no, I guess we're going to write, sorry, I don't even know what this instruction does. If register source was less than signed immediate, okay, 0 otherwise. So we're going to write it either way. We're going to write either a 1 or a 0. Thank goodness for PowerPoint. Okay? So what's that going to look like? It's going to look kind of like what we just saw. So the PC tells us where that instruction is. We read it in. We say, oh, it's an SLTI. Okay, great. That means what I've got is, register 3, register 1, and then I'm not using this register. There's nothing here. That's what X is supposed to mean. Okay? And now here's kind of the fun part. What gets sent to the LRU is the value that's in register 1. So we're going to pull that out from the register file. Okay? But to answer that earlier question, 17, where is 17 stored? Right? There are some bits that represent 17. Where are they? Anyone know where they are? Yeah. Yeah, they're actually in the instruction, right? Remember, our instruction is 32 bits. When we get an opcode that's an immediate opcode, we know that the end of that instruction is going to have the immediate value in there. All right, so if I take the bits at the end of the instruction, that's my value. So I don't even have to, I just pass those from the instruction into the ALU. Okay, it's kind of cool, right? So now I've got my two numbers. The ALU knows how to do a comparison, so I do the comparison. And then again, I skip the memory stage because I don't do, there's no memory access here. And, you know, if the expression is true, I write a 1 to register 3. If the expression is false, I write a 0 there. So I go back this way, and then, you know, my PC has been incremented, so I go to the next instruction. I read it in from memory. And this is all that CPU is doing. It's just on this treadmill. Stage 1, stage 2, stage 3, stage 4, stage 5, next instruction, right? And it just keeps doing it. Yeah?
So I just noticed your little blank box.
Oh, yeah. Mm-hmm.
PC doesn't actually get implemented until afterwards, but you set up.
No, so, well, I've got a better picture than this. So the question was, when does the PC actually get incremented? And the PC actually gets incremented right away. Okay, but the question is when, well, I don't know if the PC, actually, let's look at it, have a more detailed picture. Okay, so just hold that question of when, the question is when exactly does this PC value change? Okay, and for right now, it could happen right after I read the instruction, or it could, as long as it happens before I read the next instruction, I'm okay. So we have some flexibility. Okay? Any questions about this? Because each one, there's one more. Actually, there's two more. All right, so great. Okay, finally, right? Here you are. We've got this stage 4, and you're saying, why, oh, why, oh, why do we have 5 stages? We never use stage 4. Well, now we're going to use stage 4. Okay? So this is a store. And basically, what's this going to tell us? This says, okay, so stage 1, we get the instruction, right? Increment the PC. Stage 2, we say, okay, well, look, this is a store word. That's good. That means we're going to finally access memory. I'm happy about that. Okay, and what am I going to do? Well, I'm going to store whatever is in register 3 into the memory location that you compute, that you calculate by taking the value of register 1 and then adding this immediate offset to it, right? This 17, okay? Which, by the way, seems a little fishy to me, right? Because this is supposed to be a word, and if you're doing 17, it's not word aligned, okay? But that's our example, okay? So, you know, where do we figure out the target address? We do that in stage 3. That's in the ALU, because the ALU knows how to do adds. And, you know, what are we going to do in stage 4? That's where we take the value that was in register 3, or that's still in register 3, but we've read it, and we put that into memory. Where is it going to go? Are we going to really write it out to memory? Anyone? Are we really writing this thing out to memory? It depends. What's it depend on? Yeah, it totally depends on how we implement the cache. So if we're doing a write-through cache, then we write it into the cache, and absolutely it goes out to memory, although we might not wait for it to. Okay? If we're doing a write-back cache, then no, it just goes in the cache, and we trust the cache system to make sure that if it throws it away, before it throws it away, it makes sure it's in memory. Okay? So as far as our CPU is going, you know, it does the write to the cache, and it's done. It doesn't have to worry about it. Okay? And then there's no register update that happens here. So in this case, unlike the previous ones, stage 5 doesn't do anything. Okay? So this is it. This, you know, fetch, decode, execute. You know, this is what we do. So, you know, here's that picture again. You know, this is what we get when we decode the instruction. What goes to the ALU is the register that has our base address plus the offset, how much we're going to add to that base address. We figure that out, and then finally, we get some stuff. We do something with memory, which is we take the value that was in register 3 and we write it to that location in memory. Okay? That's stage 4. And stage 5, we do nothing, and then we go on to the next instruction. Okay? So, you know, you do not want to be a CPU, right? It's a boring life. This is all you do. You just chug through this thing, cycle by cycle by cycle. Every cycle you go through it again. Every once in a while things get interesting because you get a memory stall. You have to sit around and wait. That's not really that interesting. Okay, but that's what the CPU does. All right. Okay, so, you know, why do we have 5 stages, right? So, you know, if you celebrate Passover, this is kind of like, why do we have four, why do we do this? Why do we have four questions? Okay, why do we have 5 stages? I don't know. We have 5 stages. There are other architectures that have other numbers of stages, okay? And it's a design decision, okay? There are fancier things you could do that you might, want to add a stage to this pipeline to support other kinds of instructions, for example, okay? So why does MIPS have these 5 instructions if most of them don't? If most of them don't use them all? And the answer is, well, there's at least one that uses all 5, and that is the load instruction. Okay, so far, every instruction we looked at, the arithmetic ones, the store, the immediate instructions, they always skip the cycle. So who uses all the? They always skip the stage. So who uses all the stages? And that's the load. So here's a load instruction, right? And again, it's got this offset. So we're going to take whatever is in the memory location that we compute by taking the memory location that's stored in R1, adding 17 to it. And what we want to do is we want to load that into registers 3. Okay? So the way that's going to work, you'll notice there's no idle stages here. Okay? So the way that's going to look is we get our instruction, decode it, we compute the address that we're going to load from, we go to memory and we say, hey, give me what's at that address, and we stick it into register 3. Okay, so finally, we've used all our stages. Okay? All right, and if it bothers you that there's idle stages, it bothered the people designing these systems too, and we're going to do some work to, in subsequent lectures to take it to at least minimize the harm that would have from idle stages. Okay, so now don't get excited because I was all ready to do the clicker question, and I either lost part of it or I left it in my office. So I actually don't have the thing I need to finish this. So we're going to do, this is bad. We're going to do the world's lowest tech peer instruction. And maybe I'll take a picture and send it to Dan so that he knows we've done it. Okay, but here's a slightly more complicated version of this pipeline, this data path we've been building. Okay, and what you can see is, we get our instruction memory. We have a separate adder, right? So as you pointed out earlier, in the previous picture, I had this little box that didn't have a label on it that was adding 4 to the PC. What is that box? Well, not surprisingly, it's an adder. Okay, so it's an ALU that does nothing but add things, right? It's just an adder. Okay, so we've got one of those. We've got this other adder here that's doing what? It's taking an instruction and it's taking something from an instruction and it's taking the PC and it's possibly it seems to be updating the PC. Does anyone know what that thing's for? We didn't have that on our previous picture. Yeah, that's for branches, right? And maybe jumps. Maybe not jumps. Maybe there's probably something missing. We probably need something else for jumps. Yeah.
It just have for additional perspective, we had that 1 bit to flip between 2. So here we could have 1 bit which says either added if it's a branch, or otherwise just completely set it.
Well, yeah. So I mean, there's probably a way to do this with one adder, where what you send in is either 4 or whatever this line is. There's probably another way to wire this up. Yeah. Yeah. So this is what we're going to ask about. There's some other things going on here. So here's the peer question, which is this. We talked about these things called multiplexers, right? Remember, what a multiplexer does is it takes some number of inputs. It takes some number of selectors, right? 2 to the and it takes 2 to the S inputs. It takes S selecting lines, and one of those inputs gets to go through, okay? So the question is, here's this diagram. It's got a few more wires in it than we had before, and the question I wanted to use our high-tech clicker system for was this, which is, if you really want to make this work, how many multiplexers do you have to add to this picture, okay? And basically, your choices are 0, 1, 2, 3, or 4 or more, Okay? So why don't you guys look at that for a second, pretend you're going to click, and then maybe we'll do a show of hands. We don't do show of hands because that's intimidating, isn't it? All right. Well, maybe I'll just ask for you guys to say. So take a look. You can talk. Oh, you're not supposed to talk in the first part. See, I'm totally not a clicker guy. I'm sorry. All right, well, take a look at it. Think about it. You can talk a little bit because we're low tech. Yeah. All right, so okay, so here's where we do the first phase of the clicker. And if you really are intimidated, you don't have to participate because I screwed this up. So, but who thinks it's A? Anybody for A? See, this is why we use clickers. Okay, a couple brave souls for A. Okay. How about B? Okay, you can vote more than once because I can't tell. It's okay. You can vote for all of them, then you're guaranteed to be right. Okay, C, that you need 2 multiplexes here. Okay. D, 3. Okay, yeah, it's between C and D. Good. And anyone think there's 4 or more? Yeah, okay, well, good. That was a pretty good spread. So in the interest of time, let me show you what I think the answer is, and then we can discuss. So I think it's 3. And basically, it got down to the question that you asked, which is why I didn't answer it, which is, wait a minute, look at this. I've got a signal that's coming here. I got a signal that's coming here, right? I know enough, electronics to know that ain't going to work, right? What am I going to get there, right? It's garbage, okay? Because this thing's always pumping out some signal. This thing's always pumping out some signal. So I'm going to need one there. Okay, and everywhere that I have a multiplexer, remember, I'm going to have a control signal. So this is kind of the bridge to the next topic, which is how do we do control? Okay, because what the control is going to be doing, it's going to be the brains in the train, in the train yard that's flipping that track and flipping that track, right? It's right doing the switching. Okay, so whenever there's a multiplexer, if the right signal comes in, then the right input is going to flow to the output. So here, we're going to have to have a signal that tells us, are we going to use the PC that we incremented, right? We just took the old PC and added 4 to it, right? That's one of the signals. Or the other signal might tell us, hey, you know what? No, use this branch address, right? So in this case, if I have a branch or a jump, right? If it's an immediate, then I basically just take that address and I add that, I put that in the PC. Or if I have to do some calculation, I'm going to have to, do the addition and then send that to the PC. All right, so there's going to be a mux here that tells me, am I just going to the next instruction or am I following a branch or a jump? Okay, that's one. Let's see, what else do we got going on here? This is the one that's telling us, if you remember in the picture that we looked at before, there was always this weird line when we were skipping memory that it looked like when you were writing the register, you always had to go from memory into the register. Okay? Well, that's what this switch is telling us. It's telling us, is this like an add instruction where what's coming out of the ALU gets put in the memory in the register, or is this a load where what's ever coming out of the memory has to go into the register? So this is our switch. This mux here is going to tell us: are we doing something from the ALU into the register, or are we taking something from memory and loading that into the register? Okay. And then, does anyone know what this one is doing? So what's it doing? It's taking the instruction And sometimes it's taking stuff from this register box, and sometimes it's taking stuff directly from the instruction. So what's that mux implementing? Yeah. Yeah, that's our immediate line right there. So there's going to be a signal that says, hey, this is an immediate instruction. Don't take what's coming out of this box and put it in there. Take what's coming out of the lower order bits of the instruction and put it in there. Right? So this is all going to be set with these different with these different signals that we'll talk about next week. So let me just, I got a couple more minutes. Let me just get through. There's a couple things I want to get through so I don't have to do them next time, and then I'll let you guys go. So, just to summarize, what we're going to have is we're going to have this, just keep it down for really 2 more minutes, and then I'm out of your life for the whole weekend. So we're going to take, the opcode and some stuff in the instruction, and that's going to drive all these signals that are going to make the data flow through our data path in the way it needs to. And we're going to turn on and off those multiplexers in order to do the right function. Okay, so that's what we're going to start talking about next time. So what do we need to do this? Well, we need a place to store the program counter. We need a register file, right, for general purpose registers. We need memory, right, because we got loads and stores. Okay, we need an ALU and a bunch of adders, right, as I showed on that last slide, and we talked about how to build that. And then we're going to need some other registers, as we talked about, because you're in order to keep things as they're flowing through the circuitry, you're going to need to somehow store values. Okay, so that's kind of the hardware we need. And then the last thing I wanted to talk about just briefly is that we just have been talking about this single cycle, right? So a cycle is from this edge right to the next edge, right to the next leading edge. So we want all 5 of these stages to happen within a single clock cycle. Okay, and remember, that's going to work great. The thing that might mess us up is when we go to memory. Okay, and if our level 1 cache is doing its job, if we get a cache hit, we're guaranteed we'll complete within this cycle. If we end up having a miss in level 1, then we're going to do what's called a pipeline stall. And we're going to have to just wait here until memory responds. And if it comes out of level 2, it's going to take a certain amount of time. If it comes out of level 3, it's going to take longer. If it takes out of memory, it's going to be even longer than that. So where we're going to get in trouble with this approach is this stall right here. So another way of thinking about doing it is you can also do a multiple cycle CPU, where basically your clock tick becomes the length of the longest stage, not counting a memory delay, and then it works this way. Okay, and this is going to give us some more flexibility in terms of how we coordinate different instructions. So here's basically the things you need to think about in designing your data path, and we'll talk about these next time. And then really that was all I wanted to get through today. Hopefully I'll find the missing piece of the clicker, and we'll have a real clicker question on Monday. In the meantime, have a good weekend.